Now let's talk about the last topic of this chapter, which are logic arrays. There are two main types of logic arrays: PLAs, programmable logic arrays, and FPGAs, field programmable gate arrays. So PLAs are AND gates, or is an AND array followed by an OR array. And that kind of pattern you've seen before in our two-level logic with AND gates followed by OR gates that can implement SOP form equations. So these only do combinational logic, and the internal connections are fixed. So they're limited in that we can't perform any sequential logic, and there's little flexibility in the internal connections. FPGAs, on the other hand, field programmable gate arrays, allow us to do both combinational logic and sequential logic, and the programmable part of it, field programmable gate arrays, we can program both the function performed and the internal connections. Both are still used because PLAs are cheaper in general than FPGAs because they're simpler and they only do combinational logic. But FPGAs are common for systems where we need both combinational and sequential logic. Here's an example PLA or programmable logic array. We have our AND array followed by our OR array. Our AND array performs the products or computes the products or implicants, and then we OR those together in the OR array. So here's our inputs A, B, and C, and there's, those AND gates pick off some of those inputs, produce the implicants or the product terms, and then our OR array ORs them together. So we can easily implement equations in sum of products or SOP form. Here's some dot notation for PLAs, just like ROMs. We can use dot notation. Here we have A bar and B bar and C, A and B and C bar, and so forth. And then in the OR array, we pick off which implicants or product terms we want. Field programmable gate arrays, or FPGAs, are composed of LEs, which are logic elements. Some FPGA manufacturers call these CLBs, or configurable logic blocks. And these perform logic, both combinational and sequential. And also IOEs, or input-output elements. And these IOEs are, on the peripheral of the chip, and they're used for interfacing with the pins on the chip. Between these elements, both the LEs and the IOEs, are programmable interconnects, and these connect in a programmable way those different elements. Some FPGAs also include common building blocks such as multipliers and RAMs, just because they're commonly used by designers. Here's a picture of the general layout of an FPGA. You can see that we have our logic elements performing both combinational and sequential logic in the middle of the chip, and then we have our input-output elements, or IOEs, on the outside of the chip to interface with the outside world. So let's dive into what is inside of a logic element. So LEs, these logic elements, are composed of themselves lookup tables that perform combinational logic. So this is what we talked about when we talked about our memories, using them as lookup tables. That's exactly what the lookup tables are. They're very small memories. And flip-flops to perform sequential logic. And then we also have multiplexers that can connect these lookup tables and flip-flops together. This is a logic element, or LE, from Altera's Cyclone IV FPGA. And this is a picture from that data sheet, from the Cyclone IV data sheet. So a lot of stuff going on here. Let's focus on the main parts of this figure. So we have this lookup table, which is a small memory that has 4 inputs: data 1, data 2, data 3, and data 4. And that's a 2 to the 4 by 1 bit memory. And so it can perform any function of 4 inputs. And And you may notice that we could choose this output here from a flip-flop. So that next element there is our flip-flop. So here in green, we have our flip-flop that has a clock input here, and it has an enable input and a low asserted clear input, and then also has synchronous load and clear logic ahead of it. And so those two elements are the main elements of the LE, or the logic element. We have our lookup table and we have our register. And so on this, we have a bunch of these little multiplexers, and those control lines are configurable. Those select lines are configurable. And you can see that we can either take out from those multiplexers, we can choose either the output of the lookup table or the output of our flip-flop. And then we can, depending on how we configure those select lines, we can feed that to other logic elements. And in addition to that, there's other, there are other pieces. There's a carry chain, so this helps speed up addition because that's a common operation that designers want to perform. And there's some, additional kind of asynchronous clear logic and some routing logic here for the clocks as well. But again, the main things are this lookup table and the flip-flop, and we can choose either a sequential output from the flip-flop, or we could choose the combinational output from our LE from the lookup table. And you may also notice that this output here could also be fed back. So output from our flip-flop could also be fed back to be used in this combinational logic, depending on what the select line is for that multiplexer. And that could be useful for things like finite state machines. So again, the Cyclone IV LE, most important parts are the 4-input lookup table. That's small memory, 2 to the 4 by 1 bit lookup table, or 2 to the 4 by 1 bit memory, 1 registered output, and 1 combinational output. And we can choose between whether we want to use a registered or combinational output. Let's show how to configure a Cyclone IV logic element, LE, to perform the following functions. So we have a function of 3 inputs here, and another function of, in this case, 2 inputs. So our lookup table, we had our lookup table, which is a small memory. It could have up to 4 inputs, and we only need 3. So we're going to tie A, B, and C to 3 of those inputs, and then the last input, we can't just leave it floating, right? All inputs have to be driven to something, but we can tie it either to 0 or 1, doesn't matter, but it has to be tied to one of those. It doesn't matter if we tie it to 1 or 0, but it has to be tied to one of those. And then our lookup table can perform the function that we want. And how do we define that? Well, we'd have to write a truth table for that, A, B, C, and our output, X. And then we can just draw what that truth table is. 0, 0, 1, 0, 1, 0, blah, blah, blah. So it would have a 1 here, A bar, B bar, C, and then a 1 in the 1, 1, 0 case, and everywhere else it would have zeros. And then we would feed that through the final multiplexer as the output of our logic element. So we want a combinational logic output. Similar to that first problem, now we have only 2 input variables. We can still use our 4 input lookup table, tie A and B here, and then we can ground the other 2 inputs. We have to tie them to something. Remember, inputs always have to be tied somewhere, and then we'll choose that that combinational output is the output of our logic element. And then we would draw the truth table for what that is, 0, 0, 0, 1, 1, 0, 1, 1. And this is A and B bar. And so that would be what we would store in our, we could put 0, 0 for the other bits in our lookup table in our small memory. And so here we have it written out to data 1, 2, and 3 are connected to A, B, and C in our lookup table. And this is what our lookup table should hold inside its memory. And again, don't forget that we have to tie all of our inputs to something. Outputs can be left unconnected, but inputs cannot. So data 4 would be tied to 0. And then, similarly for y equals A and B bar, connect A and B to data 1 and data 2. And then in our truth table, those are don't cares, but not in our connections. We have to tie data 3 and data 4 to something. And we store inside our lookup table, this is what we're storing, a 1 in the 1, 0 address, or in the 1, 0, A equals 1, B equals 0 case. Now suppose we want to use LEs to perform this XOR function of 6 inputs. Well, it'd be nice if we could just use one lookup table, but we can't, right? But we can use one to do 4 AB or A1, A2, A3, A4. We could perform this lookup table on one of the LEs, can perform, that kind of partial calculation. And then we feed that through to the output of that LE, and then feed it to another LE, right, to the lookup table of another LE. And then we have our A5 and A6 on the other inputs, ground the 4th input. And now this one performs, some temporary Y1 or something, Y1 XOR A5 XOR A6. And then we feed that to the final output as our Y, as our combinational output. And so this one requires 2 logic elements because we're going to need 2 lookup tables. We can't fit in a single 4-input lookup table. We're going to need 2 of those. How many Cyclone 4 LEs are required to build a 32-bit 2-to-1 multiplexer? Well, let's think about it. 2-to-1 multiplexer, let's just draw this out, has a single bit 2-to-1 multiplexer, has a select line and 2 inputs, D0 and D1, and then the output Y. Okay, well, so to build that with a lookup table, we would need, it has 3 inputs, D0, D1, and S, the select input. And so we'd need a single lookup table to do each of those. We'd have a lookup table, we'd have select, D0, D1, the 4th input of the lookup table to be tied to 0. So that would produce one of our bits, and would need, so that's a single LE, okay, that last multiplexer to select the combinational output. And we're going to need 32 of those. So we're going to need 32 logic elements to implement a 32-bit 2-to-1 multiplexer. And the last example for figuring out how many logic elements would need to build some circuit, let's do a sequential circuit. So we have some finite state machine, has 2 bits of state and 2 inputs and 3 outputs. So how many LEs or logic elements would we need to build this? Well, 2 bits of state, we know each logic element has just a single flip-flop or single register, single 1-bit register. And so just for the bits of state would need to figure out, right, we're trying to figure out the next state. Next state. Well, we know already if we need 2 flip-flops, we're going to need 2 logic elements. So there's our 2 of our LEs. Okay, can we calculate what the next state should be with a single lookup table? Let's think about that. So what do we need to calculate the next state? Well, we need our current state, which we know is 2 bits. Okay, so there's 2 of our bits being used, and our inputs. Okay, our inputs are 2 bits. So in fact, we can calculate our next state for each next state bit with a single logical or a single lookup table. Okay, so that'll work for calculating our next state or state bits. And what about our outputs? Well, our outputs are determined just by our current state. So our current state is 2 bits, and we need 3 outputs though. So we're going to need three LEs to give us 3 outputs, 3 combinational outputs. That's a multiplexer. And so here we have 1 LE for each bit of state. And the next state logic, so that's 2 altogether, and 1 LE to compute each bit of the output. Again, we'll tie 2 of those lookup table inputs to 0 because we actually only need 2 of those inputs to determine each of the outputs. So we'll need 5 LEs together, 2 to calculate the states and to store the state in the flip-flops, and 3 to calculate the outputs. The FPGA design flow is to use a CAD tool like Altera's Quartus II or Quartus Prime, enter the design using either schematic entry or an HDL, most typically using an HDL, simulate the design, not an optional step, and then synthesize it and map it onto the FPGA. That's what the CAD tool does, and then download the configuration onto the FPGA. And finally, we'll test the design in hardware.